Okay, there we go. All right, so, oh yeah, the first thing I want to mention, next week, your demos, which team is presenting what day has been posted on Piazza, I think as of yesterday. You might have noticed that already. So that gives us about 10 teams per day, which, since we have like 80 minutes for the lecture, I think the reasonable time is to keep the presentations not longer than 5 minutes, because there is always sometimes switching and some time for questions and so on. So 5 minutes is a good time to aim for. It should be more than enough to just show some demos, say what roughly or quickly what did you do. Okay. Yeah, any questions on that? Final projects next week?
So we only present this time. I mean, do we have another presentation?
No, that's it as far as presentations go. Then you need to submit the final project. That's the May deadline, right? I forgot which day in May it is. It's online. Yeah, that's the only presentation, right? Everything done? If you need to have everything done for the presentation, the answer is no, you don't have to have done everything. That's why there is the deadline for the final submission later. But you need to have deadline. You have to have done something that you can present, right? So it doesn't really have to be the whole thing, but you should have at least some preliminary results to show. Okay, makes sense? All right. So today I'm going to cover the thing that I was always promising you. Finally, we need to talk about how to detect collisions. That's sort of the last important topic I want to cover here. Then I will have Harmony do a lecture on the hair sim, because some people were interested about that, and she implemented it last year with pretty good results. So I invited her to give a lecture, I think after the demos at some point. Okay. So what is the problem of collision detection? So in general, we are given, we can take it as an algorithm. So as input, we have two triangle meshes. Let's call them M1 and M2. And on output, in the simplest case of collision detection, I just want to determine whether they do intersect. That's the simplest case. In a more practical, more complicated case of collision detection also tells you what are all the points of intersection. So again, here we assume that our objects are represented as 3D polygon meshes. So I have a 3D polygon mesh for one object, 3D polygon mesh for another object, and I want to find out if these two polygon meshes are intersecting at some point. So either I can have the routine just tell me yes and no, that's sometimes all that I care about, and in other circumstances I need to compute all the contact points. And so the problem of collision detection has been studied pretty well, and there are several main flavors to the algorithm. So you can subdivide the algorithms into these two main pieces. So there is what we call static collision detection, so CD for collision detection, and continuous. So static means just what I wrote here. I just give you two meshes somewhere, and I need to know if there is a point where they intersect. So that's or discrete collision detection. Continuous means that these two meshes are actually moving. So the continuous collision detection considers motion of the meshes, and that's what we will discuss later, because that gets more complicated. The question there is not if the meshes intersect at the given configuration, but under some assumption of how the meshes are moving, the question is if there exists time when the meshes intersected. And what would we be most interested in, as we discussed previously when talking about rigid bodies, would be the first time of contact, the first time the mesh is intersecting. So that's a problem of continuous collision detection, which is more involved, of course, than the static collision detection. I guess I should also explain why do we care about the continuous collision detection. Like if we are simulating at 30 frames per second, isn't that like high enough resolution that we would get away just with static collision detection? You might already know the answer based on your experience, because you have done some collision detection, right? Like basic types of collision detection, like point against a sphere or a plane. That's pretty simple, right? You don't need anything fancy there. But if you do it just every frame, you might have already noticed that it's not always perfect, right? What can happen? So for example, or does someone want to tell me? Yeah, go ahead.
If you like go through the surface and like
Right.
over the time
Correct. So if I have something that's like sort of like a thin wall or something, right? And then I have some sort of small object, and if over a time step the object happens to step here, everything looks fine, right? Because there is no collision at this time, no collision at this time either. But obviously this is impossible. The object had to pass through the wall, right? So that's exactly what continuous collision detection tries to solve. So that's not what we'll be talking about today. Today we'll focus on the static collision detection, and continuous collision detection I will cover later, because already static collision detection is interesting. Now the other flavors are for rigid bodies. You can either consider the meshes to be rigid bodies or deformable. As you can imagine, if the bodies are rigid, then you can take advantage of it and pre-compute some acceleration data structures, bounding volume hierarchies. That's what you'll be talking about today, which then facilitate collision detection. Other types are inter-object and intra-object, or this is sometimes called self-collision detection. Doesn't make sense for rigid bodies, but if you have deformable bodies, then you can imagine the body being deformed so it collides with itself, right? If I have some sort of elastic bar and the elastic bar happens to do something like this, it means that collided with itself, right? So this case is sometimes considered special. It's called self-collision detection, because it's a little bit tricky, because of course you cannot just say that every vertex collides with it, every triangle collides with its neighbor, because they have to, because they are connected. So this is fine, but this is not fine, where some features of the mesh which were originally far away, and definitely not definitely not neighbors, now are in contact. So that's self-collision detection. This is where most of the most recent research is focusing on these difficult cases of deformable, self-collision detection, and continuous. But today I want to cover the basic, the easy cases, and also the most practical cases. Well, not really easy, but let's say well-studied cases. Starting with the static collision detection for rigid objects. Now we will not assume that the meshes, that the objects are convex or anything. Let's assume that they are just like the ordinary meshes you can download, like a character or armadillo or bunny or whatever. Okay, so the static collision detection for rigid objects, that's what we are going to focus on today. It's easy to come up with an algorithm that gives you the right answer, but it's not very fast, right? All you need to do is to go through all triangles from mesh 1 and all triangles from mesh 2. So I guess let me write it as a pseudocode. So for each triangle T1 from mesh 1, and also for each triangle T2 from mesh 2, then you just do triangle intersection between T1 and T2. So this is sometimes called the primitive test. In this case, the primitives are the triangles the meshes are composed from. So that will do it, right? That will correctly solve the static collision detection problem for two arbitrary meshes just by looking at all the primitives, except that's obviously quite wasteful, right? What is the time complexity of this test? That's easy to see. So the primitive intersection test has constant complexity. Those are just triangles, right? Triangle has just 3 vertices, 3 edges, 1 face. Simple thing. If you still have time at the end, I can tell you one method how to do triangle intersection. It's not very complicated. But what's the time complexity of this algorithm? The main thing always about collision detection is speed, right? Because this naive approach is not very fast at all. N squared? That's correct. Yeah, if both meshes have n elements, right? Or n triangles. If mesh M1 has n1 triangles and mesh M2 has n2 triangles, then the complexity would be n1, n2, right? Really just nested for. There's nothing special about that. And that can be a lot, right? Imagine a mesh that has 10,000 triangles. Another mesh has also 10,000 triangles, so you will end up with 100 million tests, right? And if the meshes happen to be something like, let's say this is one mesh, this is another mesh, which happens to be very similar or something like that, then it's clearly pointless to be testing, like here I have lots of small triangles, right? Here, lots of triangles over here. It's certainly stupid to be testing every triangle from here against every triangle from there, because they are already far away, right? So the first thing you can think about, bounding something, right? Bounding volume. The easiest thing, yeah, box is pretty good. Even simpler is a bounding sphere. Oh, that's not a great sphere, but imagine that's a sphere. So you can just enclose each of the bodies in a bounding volume, in this either bounding sphere or bounding box. There are other types of bounding volumes, which I will also discuss later, but sphere or box works. And of course, if you know that object 1 and object 2 are enclosed in bounding volumes B1 and B2, and B1 and B2 do not intersect, then obviously whatever is inside cannot intersect either, right? And the point is that checking for intersection between bounding volumes is very simple, right? If they are spheres, then what is the test? That's really trivial. If I have 2 spheres, every sphere has a center and a radius. So center 1, center 2, radius 2. How do I test for intersections? Because this stuff is relatively simple. Yeah, we just compute the distance between the 2 centers, right? So C1 minus C2. Then I will look if that's smaller than R1 plus R2. That's my collision test, right? So this is really inexpensive to test this once I have already pre-computed the bounding volumes. So we will talk about the different types of bounding volumes. There is like an interesting zoo of bounding volumes that are often used in collision detection. So we will discuss that, but we'll discuss that later. First, we will discuss how exactly do we want to use the bounding volume. So this is the basic thing you could do, just bound the objects in a single bounding volume. Just pre-compute single bounding volume, and that's it. Now the problem is that this is not enough, right? Like imagine that I have 2 objects which look like something like this. I will do something more abstract this time. And here is another object. So they actually are intersecting, right? So it's not like an easy case. When things are far away, collision detection is really easy, right? Because already some simple bounding volume will tell you, okay, these are far away. You don't have to do a lot of computations there. Now, cases like this are a little bit more tricky when there already is, or even when they were close together, right? Because I can have non-convex objects. So in theory, I could have one object that looks like this, another object that happens to look like this, and they are not intersecting, right? But certainly no simple test like this will quickly give me a certificate that they are not intersecting, right? So what I can do in these more complicated cases, huh? Level set would be one idea, yes, that's true. There are several approaches to collision detection, so that would be one of them. The one I want to talk about today is a hierarchy of bounding volumes, which is probably the most commonly used one. The other possibility would be subdivision of space, spatial subdivision, like spatial hashing and so on. Some game people I know are using that because it has some advantages, but I still think that the bounding volume hierarchies are probably the most standard approaches to solve that. So what is the idea of a bounding volume hierarchy? Well, okay, so here, what happens in this configuration? So if this is my mesh M1 and this is my mesh M2, of course, whatever bounding volumes I give it, right, if there are bounding spheres, the bounding spheres clearly must be intersecting. So that means that this test on the bounding volumes, if they intersect, is just wasted computation, right? Anytime the intersection test is negative, it tells me the bounding volumes are intersecting, then I have not saved anything. In fact, I have wasted time for doing the actual test, right? It's like not that big of a deal because the test is so quick that doesn't matter so much, but that's what it is. So what can we do? Well, we can apply the same idea recursively, right? Computer science, somebody said that computer science basically is taking some mathematics and combining it with a tree. So that's exactly what we use here. So we apply the idea recursively. So because one single bounding volume on this object M2 that it didn't cut it, then I can try covering it by 2 bounding spheres or 3, like this, right? And if I do that, then this second bounding sphere ends up being actually useful, right? Because this smaller bounding sphere, it's not as good as the big one, but the smaller bounding sphere does not, of M2, so let me call it, I don't know, B2, that does not intersect M1, right? Which means this bounding sphere B2 gives me a certificate, gives me a guarantee that no triangle from M1 can intersect any triangle which is contained in B2. So it means that if I consider it as looking at all possible pairs of triangles, I can discard a pretty significant chunk of the space of all possible pairs by doing this, right? And this is essentially the idea of constructing bounding volume hierarchies. So let me do it more justice by explaining it properly. Bounding volume, oops, it's to my hierarchies, or BVH, sometimes you can find that acronym. By the way, these bounding volume hierarchies, they don't care if these are really proper triangle meshes, if they're like manifold and watertight and all these things you may want from a mesh. Bounding volume hierarchies work even if you have a polygon soup. If you have basically disconnected triangles, that's sometimes called polygon soup because you can have like non-manifold edges, right? They can have like 2 triangles, then there can be like a third one sticking out of it. Doesn't matter as long as bounding volume hierarchies are concerned. They only care about the individual triangles. Well, and the idea is to apply the bounding, to construct recursively a hierarchy of bounding volumes. So if my object looks like this, then I start by constructing a bounding volume for the entire object. We'll be demonstrating it with spheres, but it works with any other types of bounding volumes, and I'm going to discuss the types of bounding volumes later, so keep in mind it can be any bounding volume, box or whatever. So I construct the bounding volume for the entire object, then I cut it into 2 pieces. I pick some cutting plane, and I cut it into one piece and another piece, and each of the pieces I bound separately by separate bounding volumes. Something like that. And I applied the idea recursively. Then I cut whatever I had in one of the halves, again bounded by a bounding sphere, and so on. So let's see. Here is an algorithm. It's an actual algorithm. I figured that doing this in handwriting might be annoying. Is this readable? You know what I can do? I can actually zoom on it. Huh. Not here. Maybe I can do it here. Oops. Huh, it's funny. Come on. How about that? Yeah, so this is an algorithm how to construct bounding volume hierarchy for an input triangle mesh, which could really be a soup, right? Or soup, polygon soup. And this creates a tree. In this case, it's a binary tree. You could also create n-ary trees if you wanted to. I don't think there is a huge reason, there's a significant reason to do non-binary trees. So first, so this is really like computer sciencey thing. So we like start allocating a node. What these lines mean is that the BM means compute BV. So maybe I could write it like compute BV from M. This is what I mean by the capital B of M. Compute the actual bounding volume for the geometry of M, for the actual triangles represented or contained in M, and I assign it as the bounding volume of P. So I guess this you could also write as like some sort of P dot BV if this P is like a structure or class and contains a bounding volume. So this is almost like a pseudocode really. Then I split M according to some splitting rule into two pieces, into left and right piece. So that's what I shown before on this tree example. I just basically I take my polygon soup and I just chop it in two halves. Using so the simplest way you can do it, you can just find an axis aligned bounding box of the geometry. You can find the longest edge of the bounding box and say, okay, I'll split it in the middle there. There are like several ways how you can do the splitting. There are some heuristics. But it turns out that this simple one seems to work as well as anything, so as good as anything. Now, don't quote me on that, but might not be far from truth. Now, the next step, number 4, that's to check if we are not already done. Because if I'm already at like individual triangles or small enough pieces of the polygon soup, which I don't want or can't further subdivide, then I just say, okay, I don't have any children anymore. That's gonna be a leaf node, and I return. Okay. Now, if that's not the case, that means that both parts of the mesh are of the subdivision are non-empty. That actually my division, my splitting was successful. It really split it into two pieces. Then I just call recursively the routine on the left part, the ML part, and on the right part, MR part. And those are going to be my left and right children. So this is a recursive call to the same procedure as the build tree. That's the procedure build tree. So go back to my tree example. Ooh, too much. Oh wait. Good. So the algorithm is then called recursive. So starts with this one big sphere, right? And it's recursively called on like I divide this mesh into like this one piece, the top part of the tree or mesh, right? Then again, find a bounding volume for that. Then again, split it in two, and so on. Does that make sense? It's sort of cute, recursive bounding volume hierarchy construction. Here is an example how it works on some mesh I played with when I was working on my PhD thesis, or when I was a PhD student. Let me zoom it again. You can see a little bit better. It's sort of cool, this zooming. Ooh, no, that's too much. It's not super beautiful, but you get the idea. If this is my mesh M, so what I'm doing here, so this creates a tree, right? And what I can do is look at spheres at a given depth of the tree, right? So for the tree example, I showed the sphere at depth 0, 0, the root one, and at depth 1. Those were the two big ones, right? And if I look at some deeper depth of the tree, then what I see is just covering of the object by smaller and smaller spheres, right? So this is some depth. I forgot what it is, maybe like 4, and this would be 5, this would be 6, something like that. The idea being that the spheres are getting smaller and smaller, but their union always covers the object, right? And they have the hierarchy that you know which bigger sphere contains which smaller spheres, that they basically partition the object. There was some go back button would be useful. So this is what you get by calling this algorithm. It works fairly well. And again, I used it here for spheres, but it can work with any type of bounding volume, right? Just this compute BV, that can be anything. Maybe since we are using spheres right now, a logical question would be, how do we find the smallest enclosing sphere for a set of points? So first of all, we don't have to worry about triangles. We only need to worry about the vertices. Because why? Because sphere is convex, right? And triangle is convex. So certainly if the points are contained in the sphere, that all convex combinations of the points of the vertices of the triangle also have to be in the sphere, just from a convexity, right? Because all the bounding volumes, all the bounding volume types we will be considering, they will be convex. Doesn't make much sense to use non-convex bounding volumes, I believe. So all we need to care about are the vertices of the triangle. So how do we find the smallest enclosing sphere for a set of points? I have a set of points somewhere. I need to find the smallest sphere that encloses them. Do you know? Do you have an idea? It's slightly tricky. That's a very good idea. That's how I would do it as a first shot anyway. The thing is that this gives you usually a pretty good sphere, right? So let me repeat it also for the record. So the idea is to just compute the center of mass of these points, and then find the point that's furthest from them. That's my radius. Draw a sphere around it. That's my bounding sphere. So this will of course give you a valid bounding sphere, no questions about that. The problem is this doesn't have to give you the smallest bounding sphere, right? Usually it's not so bad if the points are well distributed, but you could imagine some pathological cases like this, right? Like imagine my set of points has like 1,000,000 points here and 1 point here, right? So in that case, my center clearly will be here, and the bounding sphere will be like unnecessarily big, will be like this. Oh, sorry, it's a terrible sphere, but you get the idea. Of course, the smallest bounding sphere should be like this, right? So it turns out to compute the actual exact smallest bounding sphere is not a completely trivial problem, There are some algorithms that can do it, but they get a little bit complicated. There is one, I believe there is one famous by O'Rourke. So the pragmatic advice is not to worry, not to worry about finding the best possible smallest enclosing sphere. There are also some approximate algorithms which you can use, because the point is you don't really need the smallest one, right? It's sort of nice to have the smallest one so that you are not covering any space you don't need to. But if the bounding sphere is a little bit bigger, that's fine, right? What implications will that have if I use the big one instead of small one? Just some potentially unnecessary collision tests, maybe some unnecessary primitive test I will have to execute, right? So that means it's only performance penalty, it's not a correctness penalty, right? So from performance standpoint, if you spend a lot more time to compute the perfect bounding spheres, maybe that would not even be worth it. Well, except that the bounding volume hierarchy construction is usually like a pre-processing. You do it once and then you just keep reusing it all the time. Yeah, and for the splitting strategy, that's what I meant by the step 3 of the algorithm, split M according to the chosen splitting rule. The splitting rule that turns out to work fairly well is, as I said before, to enclose all the points in an axis-aligned bounding box. So that means bounding box which has faces aligned with the coordinate system, whatever coordinate system you are using. And then just say we will split it in the middle. So if this is my AABB, then I just split it in the middle. Okay, so the next thing is, once we have computed this bounding volume hierarchy, then the next step is how do we actually use it for collision detection, right? So we will assume that now we have two objects. So now we have two meshes, just like we started with. We have two meshes, M1 and M2. And let's assume that we have pre-computed bounding volume hierarchies. Let's see, I guess, how would I denote them? Let's say BM1 and BM2. And let's assume that the meshes are not deforming, that they are just rigid bodies, which means that I can just rigidly transform the bounding volume hierarchies. Okay, for some types of bounding volumes, even rigid transformations are not so trivial, but for spheres, they are, right? Because if I rotate the rigid body, what happens to the sphere? Well, nothing. Sphere is rotationally invariant, right? Now with boxes and the like, I have to be a little bit more careful applying rigid transformations. But let's not worry about that yet. Let's just assume that we have two bounding volume hierarchies computed for our two meshes, and the question is how we can take advantage of them to detect collisions quickly. And the idea is just as I demonstrated on this drawing here. The idea is basically to test the topmost bounding volumes, the bounding spheres in this case, and if they do intersect, then just descend in the tree and try the children, right? And if I'm lucky, I will find a child which does not intersect the current node, the current bounding volume from the other tree, from the other object, and in that case, I'm in luck, then I saved a lot of primitive tests, right? And it turns out that if you keep doing that recursively, then this other sphere, let's call it B3, that was intersecting this sphere, I don't know, A1, but then you recursively subdivide it again, right? So you would again subdivide into two smaller ones. So eventually, the algorithm will actually focus the primitive tests only on the critical region, only on the region that really matters there, which is quite cool. So basically, of all these n squared or n1, n2 tests, the algorithm will end up doing really only the useful intersection tests. So how does the algorithm work exactly? Let me see. Yeah. So here is the algorithm. I can zoom it a little bit. So the objects are, I assume that they are represented as the roots of the bounding volume hierarchy tree. So those are the R0 and R1 represent the bounding volume hierarchies for the first object and for the second object. And this is only the simple case where the algorithm only tells me yes and no if they do collide or if they don't. We can then discuss how would this algorithm change if we wanted to actually output all the intersection, all the contact points. The idea would essentially remain the same, it would just become a little more complicated. But let's focus on the simple case first. So the first thing we do, we just test the bounding volume of R0 against the bounding volume of R1. So that's this B notation. That means retrieve the bounding volume of R0, retrieve the bounding volume of R1, and test if they are disjoint. So whatever bounding volume type we are using, we need to test if they are intersecting or not. As we said, for spheres, that's really simple. All we have to do is compute the distance of the centers of the spheres and compare it to the sum of the radii. Right? Trivial. Now, if they are disjoint, then we are lucky. Then we can just say no and skip all the subsequent computations, which this naive algorithm would otherwise do. Right? That's the case when we are really saving, when we are discarding. If the bodies are really far away, this test is basically the first test that's being done. Right? Do the bounding volumes corresponding to the root nodes, do they overlap or not? If not, done. End of the story. Don't intersect, right? That's this no. Now, more interesting. Well, if they do intersect, then what do we do? It depends what type of node R0 and R1 is. So if we have already descended all the way to the leaf nodes, where we could not subdivide anymore into two parts, like at the very least you will get to individual triangles, right? Because individual triangle you cannot really cut into two subtriangles anymore. I guess you could, but then you'd be creating more triangles, so that's not the point, because you need to test two triangle meshes to begin with. The leaf nodes can, and sometimes it's useful, contain more than one triangle. Sometimes you don't want to go to like individual triangle level. So in general, if both left and right are if both objects are already at the leaf nodes, then you just invoke essentially this type of test. All primitives from one node against all primitives from the other node. Just really invoke the triangle-triangle intersection tests. Okay? And the answer is obvious. You just say yes, collides if any pair intersected, and no otherwise, of course. Now the other cases, the line 7 and 9, they basically decide where to descend. So, this means if one of them is leaf and the other one is not leaf, so this R0 is a leaf and R1 is not a leaf, then it means I cannot subdivide R0 because I'm at the end of R0 already. There is nowhere to go. That's the end of the hierarchy. But I can still go in R1, right? So in that case, I recursively call the same procedure, the call test procedure, on the children, the left child, that's the LR1, and the right child, that's the RR1 of the second object of the R1 node. Okay? Now the case in line 9 and 10, that's the symmetric situation to it. That means that if I am in the leaf in R1 and not in the leaf of R0, then I subdivide the R0 nodes. And then I look at the left neighbor of R0, the right neighbor, and do the two tests there. Recursively call the same procedure. Okay? And the most interesting case is the last one. where both of them are not leaves. So I can decide in which object I will be descending to lower levels of the hierarchy, because that's like the case at the very top, right? When I find out that the root bounding volumes do intersect, then I need to decide in which one I will actually descend first, right? Because there I have a choice. Neither R0 nor R1 are leaves, so I can decide in either R0 or R1, right? And so you can do pretty much whatever you want. Again, the useful heuristic is that you just pick the node with the larger volume of the associated bounding volume. So basically that means you take the bigger sphere and say, this is where you want to cut. That's where we will descend. It sort of makes sense because you want to keep the both partitions balanced. You don't want to be testing two small objects against two big objects from the other body. And this last line basically says that whatever object I picked here, that's where I descend, and in the other object I just stay in the node I currently am. So I guess I could draw it like this, like the last case. If this is my R0, this is my R1. Now this has both left child and right child. This also has left child and right child, right? But let's say that R0 has the larger volume. Well, then I call the procedure recursively on this pair and this pair. So I descend in this tree, right? Then in the recursive call, most likely what is going to happen that I will be subdividing I will be stepping down in R1, so then I will be calling on this and so on. But that's really guided by whatever is intersecting there. Does that make sense? So this algorithm is pretty good because what it essentially does, it lets you focus on the region of contact quickly, and if there is none, then it usually quickly discovers it. Of course, you can imagine some complicated pathological cases like this one, where the algorithm will not really be that effective, right? Especially if these things are really thin, that if everything is in close proximity, then this idea of using the bounding volume hierarchies or any other collision detection acceleration is not as effective, of course. But these things are not occurring so often in practice, so that's usually not that much of a problem. I guess in theory it means that even with this acceleration, the worst case time complexity would still be quadratic. Because it must be, right? You can have a quadratic number of collisions. So if you are reporting all colliding, all contact points, then you really have to report at the worst case a quadratic number. But the thing is, this is about practical cases, and in practice this algorithm works fairly well. And can be even extended to the case of deformable objects, interestingly enough. The problem there is that you need to update the bounding volume hierarchy somehow, and there are several ways how you can do it. You can either recompute it from scratch, which you usually don't want to do because that's the slowest thing, because recomputing it from scratch means invoking this algorithm 2.1 again. The other thing you can do is just update the bounding volumes based on the deformations of your object, which is faster. It doesn't have to give you as good quality bounding volume hierarchy as the original construction algorithm would, but usually it's pretty good and it can be done much faster. And there are some specialized algorithms which take advantage of a deformation model, like subspace deformations or linear blend skinning, which can recompute the bounding volumes even faster for deformable objects. So I just skimmed through this. I don't mean to cover this in great detail, but I just wanted to tell you that there are algorithms out there to do that, if that's what you needed. If you are simulating a deformable object and needed to detect collisions against it, like for example a character walking and you need to collide it with a different character or something. Okay. So let's discuss now a little bit about the types of bounding volumes. That's sort of fun. Because there are several types of bounding volumes and each of them has some advantages and some disadvantages. There is really no clear winner, depends on the application. So let's talk a little bit about bounding volumes. So bounding volumes need to be convex, because if you don't have convex object, oh, I'm sorry, I don't see nothing. Okay, there. So we always want them to be convex. And that's because for non-convex objects, the collision detection would probably get quite tricky. So there is a spectrum. So let's first discuss about the obvious ones, I guess. So sphere clearly would not work so great on a thin object like this, right? This would be the, if my object is like this, then even the smallest enclosing sphere will clearly cover a lot of unnecessary space, right? So the things we need to balance on bounding volumes is the tightness of fit, how well it can enclose the object, and that often goes against the speed of intersection test. So in that sense, the sphere is the simplest bounding volume because it doesn't really give you a very tight fit, but on the other hand, it gives you very fast intersection test. So there are always these trade-offs. And I guess you could put all the or the often used bounding volumes on like the scale. So if you assume that the simplest one is the sphere, which it is, then the most tight convex, what is the tightest, what is the smallest set enclosing a given set of points, which is still convex? Of course, yeah. That's the end of the spectrum. That's computing the convex hull, right? Now the problem is that intersection between general convex objects, because the convex hull can be a general convex object, obviously, is certainly much more complicated than intersection of two spheres, right? Do you know how to do intersection of two convex objects? There are algorithms out there for this. If you want to do, there are sort of efficient algorithms for convex objects. There is a GJK algorithm, Gilbert, Johnson, Gierthe, these three guys test. This is three guys test for intersection between two convex polyhedra. It's sort of a smart algorithm and it's pretty fast, but it's certainly much slower than sphere-sphere intersection, right? So convex hulls are rarely used for collision detection because what it buys you in terms of tightness of fit is usually not worth the penalty of the slower intersection test and also like having to code it all up and make sure that's correct, right? And there are some interesting bounding volumes in the middle. So axis aligned bounding box, that's what you were already suggesting, is very, very nice. Another case of bounding box is oriented bounding box called OBB. So that means OBB is a box which does not have to be axis aligned. It can be oriented arbitrarily. And another interesting case is what's called KDOP, K-discrete oriented polytope. So I will explain those in a little bit. because they are all practical collision primitives. Something about the sphere? No. So let's talk for a second. So this was the sphere. There is not much to the sphere. Now the tricky thing about sphere is finding the minimal enclosing sphere, but let's leave that for computational geometers. So axis-aligned bounding box is basically just a Cartesian product of 3 intervals if you are in 3D. So this is like a start and end point. Oh, it was supposed to be E3. So it's the point. It's really a box aligned with my coordinate axis in whatever coordinate system I use. The point being that all the boxes are in the same coordinate system, right? So to compute the smallest AABB, how fast is that? How complicated is that? Again, I have a set of points, and I want to. Yep. Yeah, of course, it's a linear time, and it's also a very simple. Yes, and it's also a very simple algorithm, right? Because all you need to do in every coordinate in the x-axis, y-axis, and z-axis, you need to find the minimum and maximum, and that's it. That gives you these intervals, right? So certainly, like, no complicated geometric optimization problem like in the case of minimal enclosing sphere. It's really simple. You just basically push the planes from both sides. What you get is the smallest AABB. And how about the intersection test? So if I want to intersect one AABB against another AABB, and as I said, we assume that they are both in the same coordinate system, right? They both are using the same axes. That's what makes it really simple, right? Because all you need to do is test the intersection in all the 3 axes. Test the x-axis for intersections, the y-axis and z-axis, and that works perfect. And it's very, very simple. Now the slight problem is if it's a rigid body and the rigid body rotates, then the axis-aligned bounding box stops being axis-aligned, right? Or becomes aligned with different type of axes. So what you would need to do is recompute. If you really want to adhere to the AABB intersection test, then you will need to recompute the intervals for the rotated object. Now AABBs typically are tighter than a sphere. Like imagine for this, if I wanted to do AABB, that would be perfect, right? That would really fall into one small box. But you can easily imagine case where AABB is problematic, right? Something like that, because then the AABB will give you this. It's again a little bit wasteful. And of course, sometimes even the sphere can be tighter than AABB. Like if you have something that's almost sphere, right? And certainly it will be better enclosed in a sphere than in a box. So if you have situations like this, or if you need to rotate your objects, that's when you start thinking about oriented bounding boxes, or OBBs. So OBB is just like an ABB, except that you get to pick your coordinate frame arbitrarily. So one way you can think about an OBB oriented bounding box is these 3 intervals plus a coordinate system, or even either just a coordinate system, and on every coordinates you give it like a span, like minus cc, like the how far does it stretch on each coordinate axis with respect to some center. So this would be like my center of the oriented bounding box, and then it stretches by some distance up and down in the x direction, y direction, z direction. Okay? So how about constructing smallest enclosing OBBs? Is that simple or is that tricky? So in AABBs it was simple, right? In OBBs, what do you think? In OBBs it is tricky. There is no simple exact algorithm Oh, this is the hierarchies algorithm. Yeah. There are algorithms which are exact, but they get a little bit tricky. What is typically used for in the context of collision detection is just an approximate algorithm, which is based on principal component analysis. If you have like some sort of cloud, if you have a cloud of points, the first thing you can find is the mean. Again, it can have all the problems mean has, right? If I have like million points at one location, they will of course throw off the mean. And what PCA gives you are the principal axes which maximize the projected variation. So in this case, it gives you something like this, which are then decent axes to align your OBB with. So what that means is you do, I guess you probably had it in some linear algebra or statistics or something like that. You compute, after subtracting the mean, you compute the covariance matrix of the points. You compute the eigenvectors of the covariance matrix. Those are the principal axes of the point set. And you say, okay, those are the that's the frame for my OBB. That's what usually works. That's what usually used, I believe. Yeah, that's what usually used. Okay, how about OBB intersection? That's also a little bit tricky, because now we have to intersect two boxes, but each of them is in a different orientation, right? So I guess in 2D, like I have one box like this, another box like that, and I need to find out if they are intersecting or not. Now, there are some important results from geometry or computational geometry, which make this test exact possible quickly without compromising anything. So the result I am referring to is known as SAT, which stands for separating. There's like lots of acronyms. This separating axis theorem. And what the separating axis theorem says is that if I have convex sets C1 and C2 convex, they can also be an arbitrary dimension, but here we only care about dimension 3. Then it's true that if C1 intersection with C2 is empty, so if C1 is not intersecting C2, then there exists separating plane. So what this theorem says, that if I have two convex objects, one and another one, they are both convex, and they are not intersecting, then I can always find a separating plane between them. A plane such that one half space contains one object and the other half space contains the other object. So this is my C1, this is my C2, and this, by the way, works in any dimension. It can be dimension 1,000,000, it still works. Now, if my convex sets are polyhedra, then there is even more. I can say that there is a stronger version of the separating axis theorem. So if C1, C2 are polyhedrons, then I can say more. Then I can say that there exists a separating plane which is either parallel, which is parallel to either a face or pair of edges. So this is a stronger version of the theorem, which further restricts, which tells me something about the separating planes. So I don't have to search for all possible separating planes, I need to only consider a finite subset of separating planes, because this is how I'm going to use this theorem to detect intersection of two OBBs. This theorem tells me that all I need to do is to look for intersections or look for separating planes. Look for separating planes which are either parallel to a face or a cross product of two edges, one edge from each bounding box. So this turns out, this gives me a total number of 15 axes which I need to test. Let me show you why 15. So this is, we are talking about OBB intersection test. And from the SAT theorem, we know that we only need to test separating planes which have either the normals, either the face normals from the one OBB, the face normals from the other OBB, or the cross product of the edges from one with the second one. So this is a total, so there is 3 faces in the first OBB, if we are in 3D. There are 3 faces in the other OBB, because that's in a different orientation. And if I take any edge from the first OBB and any edge from the other OBB, that's 3 by 3 directions I need to test for. So that's a total of 9 plus 6, that's a total of 15 directions I need to test. 15 normals of the separating planes I need to test. And if I know the normal of the separating plane, let's try this one. The way I test is very simple. So if this is the direction I need to test, this is the normal of my separating plane, then what I do, I project on this line and test if it intersects, right? So in this case here it intersects, which means I don't know anything, because what I'm looking for is a separating plane, right? But if I take this direction and I project, wait, which one? Yeah, like this, right? If I take, how do I draw it? If I take this one and project here, then I found intervals which are not overlapping, which means that I found a separating plane, right? And clearly finding a separating plane ends the discussion, because that proves that the two sets are not intersecting. But thanks to the SAT theorem, if I test all 15, all these candidates, and I don't find a separating plane, then I can conclude that they really are intersecting. So this test really is perfect, which is an interesting property of OBBs, or I guess which is the reason why OBBs are practical in collision detection. The final type of bounding volume I wanted to mention is KDOP, the discrete oriented polytope, which is also sort of interesting. So first I need to define what is a slab. So slab, which slab number I will define as a set of vectors such that the dot product of x with some normal ni, which is the parameter of my slab. So the parameters are d1, d2, and normal. Maybe I'll give this like a vectors. So I look at the dot product between normal and the x. I assume that the normal is a unit vector, so let's assume that the length of the normal is 1. And I'm looking for all the vectors such that the dot product is in a range from d1 to d2. So what is it? What is a slab geometrically? Well, it's basically an intersection of two half spaces with parallel planes, right? So this is if this is my normal n, ni, then the distance d1 cuts one piece of the slab, and the distance d2 the other one. Is that clear, or do I need to explain why this works? So let me explain real quickly. So the thing is, I have some coordinate system somewhere, right? And if I have some vector x, by taking the dot product with ni, what I'm looking at is this length, right? And if I say that this is d1 and this is d2, which means that this set basically picks this slab of vectors. That's what's happening there. You look confused, but you should not be. So the main question here, where do I take the normals from? So if I say that these normals, so let's say that my normal 1 is 1, 0, 0, my normal 2 is 0, 1, 0, and my normal 3 is 0, 0, 1. So this case is sometimes called 6-DOP, because I have only 3 normals, but every normal defines 2 planes. So that's why I usually multiply this by 2, and 3 by 2 gives me a 6-DOP. So what is a 6-DOP? Yeah. Yes, it's just 6-DOP is a synonym for AABB, right? Because AABB was, that's exactly what AABB was doing, right? It was taking slabs in planes with normals given by the coordinate axes, x, y, z. So that's exactly this. So the one way you can look at KDOP is essentially generalizing the idea of AABBs to give AABBs more power, right? So one way you can look at it, that one way to avoid this problem of AABBs, if you have something diagonal, the AABB is like stupid big. One way you can avoid it is by doing OBB, by rotating the box. The other way, you can do a more general KDOP. So essentially, you can give it more normals, you can give it more cutting planes, which restrict which tighten the bounding volume. So the popular choices would be, for example, this. You could set the normals from this set. Again, I assume we are in 3D. So add these four more normals. So with these 3, that would lead to 3 plus 4 is 7 times 2. That would be a 14-DOP. Do you know what these 4 would do? They essentially correspond to cutting corners. Right? So I guess in 2D I could draw it like this. So this is what an AABB in 2D would give me. And if I allow these additional directions, oh, I guess I didn't really write it explicitly. Okay, I should maybe that's why you are confused. The definition of a KDOP is that it's, I take this for granted. It's the intersection of the slabs, right? So in this case, in the case of AABB, I have 3 slabs in the X, Y, and Z coordinate directions. I intersect them together. That's my KDOP, right? With the more general KDOPs, it's the same idea. I just take more slabs with different normals and I intersect them. So in this case, I'm taking these vectors. This vector in 2D would be just this one and this one. So it basically means that I can cut the corners away. And this is what remains, right? This would be my 14-DOP. Another popular choice is to cut the edges, which is basically this, which you take these normals. 1, 0, 1, 1, -1, 0, 1. So this basically means cut the edges. This would lead to 18 dop. And you can also put all these things together, of course, with these basic ones, and you will get the 26 dop, which is the most dop, which is practically used in collision detection, that cuts both edges and corners. And that can get already pretty close to the convex hull.
So you could add as many normal access.
Yes. As a matter of fact, what is another definition of convex hull is, it would be like an infinite dop, right? If you intersect all the slabs in all possible directions, then you get exactly convex hull. That's another definition of convex hull. Okay, so and this is so computing a minimal enclosing dop is easy. It's just as easy as minimal enclosing A, B, B. You just have more intervals where you need to compute the minimum and maximum coordinate. The intersection test, you can do either exact intersection test using SAT, just like we did for OBBs, or you can do just an approximate intersection test. Approximate means that you only test the separating planes in these directions, which means that you can sometimes declare two dops as intersecting even though they are actually disjoint, which is again fine because that's okay, right? The intersection test only needs to be correct when you are saying these things are not intersecting, these things are disjoint. Then it must be absolutely sure. But if it's saying that the bounding volumes are intersecting, then it doesn't have to be completely sure. It can be wrong. Because if it's wrong, then it's discovered later in the collision detection process. It only means that you pay for it by more computation. So with dubs, usually you use only the conservative test. So it means you project only on these normals. Okay, and I want to also spend just a few minutes telling you how to do the primitive test, the triangle-triangle intersection test. I will not have time to discuss it in excruciating detail. That's why I'll refer you to this paper. There was a lot written about triangle-triangle intersection test. I believe this is the most commonly used method by Thomas Akinine Miller. And the basic idea is relatively simple. So here we have just two triangles and we need to test them for intersection. Maybe I could just use. So first you do again some sort of quick test to find out if these triangles can possibly intersect. So again, if I draw it in 2D, you basically, every triangle defines a plane. So let's say this is triangle T1, this is triangle T2. In 2D, those would be just lines. And you test if the second triangle does not happen to lie in an entire subspace defined, in the positive subspace or negative subspace defined by the plane of the other triangle. Because if it does, it means that the one triangle is entirely on one side of the other triangle, so clearly they cannot be intersecting, right? You do the same test for the other triangle, because sometimes you can have situations like this, right? You can have T1 like this, and you can have T2 like this. So if you are testing T2 against T1, it tells you, well, one point is on one side, the other point is on the other side, so maybe they are intersecting, I don't know. But if you test T2 against T1, then you clearly see that T1 is completely on one side of T2, so there can't be an intersection, of course. Interestingly, if both these tests fail, if both of them say, oh, maybe there is an intersection, then what it means is that there is a line, that the planes have to meet in a line, that they intersect in a line. So the triangles can only intersect along a given line. the line is the line of intersection of the two planes, so you can compute the intersection of the two planes, and then the rest of the test is to determine if that in this line the triangles happen to intersect. So I guess that's shown on this picture here. So here we have the two planes of the two triangles. There is the line of intersection of the two planes, and either the two triangles do intersect along this line, or they are separated. So the way you find it, you find what is this line, you project the triangles on that line, and then you do again just interval test. And that's not quite it. There is like still lots of details to it, and there is like tons of optimization tricks because the primitive test is being invoked all the time, so people optimize the heck out of it, and that's what's explained in this paper. But I just wanted to give you a rough idea or an overview of how it works. Okay, any questions on the basic collision detection things or your final project demos? Okay, in that case, I'll be looking forward to seeing your work next week.